Okay, so we discussed in the previous lecture how we can find the property of superheated vapor. One of the way was ideal gas equation, that's what we discussed. The other way being the property table, and next one is using compressibility factor, okay, which shows a measure of deviation from ideal gas behavior. So this is another way by which we can relate the property in superheated vapor. So this compressibility factor G um, accounts for the deviation of real gas from ideal gas behavior. So how much variation you have as compared to ideal gas. So not all the gases are ideal. So you cannot use ideal gas equation for any gas. So for real gas, we need to make some adjustment, and that can be done using the compressibility factor. Okay, and the way we define compressibility factor is, so you have, instead of PV RT, which is ideal gas, we have PV GRT. So this is an additional term. So if this value is equals to 1, then it becomes an ideal gas. And for real gases, the value of compressibility factor is either greater than 1 or it could be less than 1. So the value of G, if it is away from 1, then we better don't make use of ideal gas equation, because there is much deviation from the ideal gas. So you need to understand that the ideal gas equation cannot be used for any gases. It holds true for ideal gas, and it becomes an ideal gas. The property is close to ideal gas when the compressibility factor is close to 1. Okay, so if you write this as V ideal, so PYRT, so this becomes V ideal. So this is another way of defining the compressibility factor. So as I just said, if it is far away from G unity, if it is far away from this one, then it becomes evident that the properties are far away from ideal gas behavior. Okay, um, in most of the cases, um, for the gas to be considered as ideal gas, needs to have low pressure and high temperature. So if you have a low pressure, then and high temperature, you can, most of the time you can treat as an ideal gas, and you can use ideal gas equation. You don't need to take into account the compressibility factor. Uh, but if it is a high pressure, and so in that case you cannot use ideal gas equation. So that's the key. Now we are saying um, high pressure, low pressure and high temperature. What does that mean? That's very important to understand. High pressure and low pressure, or high pressure or high temperature or low temperature, are always in this case um, compared to the critical temperature. And what is critical temperature? I think we saw in um, let's say in TB diagram. So this is what it looks like for a pure substance in this value. So this side is a saturated liquid and this side is a saturated vapor. The point of the intersection is called the critical point, and the value of the temperature at this point is called the critical temperature. The value of pressure is called the critical pressure, and also the specific volume, which is critical. So these values can be obtained from, these are the standard values. So for a given substance you have a specific value of critical temperature, critical pressure. So we can get this value from the table A1, from the table A1. Okay, so I'll show you where we can find it out, but remember, the key point from here is you cannot use the ideal gas equation for any gases. um, it is The ideal gas equation can be used mostly when you have a low pressure and high temperature. But what is low pressure? What is the word low or high? It is always compared to the critical temperature pressure. That's very key, important here. Okay, so that's why we call as a reduced pressure, which is as compared to the um, critical pressure. So reduced pressure, this is a reduced pressure are defined as compared to the critical pressure. So pre-critical P, so this is reduced pressure. Reduced temperature is again as compared to the critical temperature T. So this is what we call the temperature corresponding to this point, the intersection of saturated liquid and saturated vapor. Um, uh, so that specific point, the variable value we call as critical temperature and pressure. And we can also define the reduce specific volume. Again, in this case, the table in the table, the critical pressure and temperature values are given. So we try to derive in terms of critical pressure and temperature. So V reduce is V by V critical, and V critical is, you can write in terms of using the ideal gas equation. You can write in terms of, so you could say P critical is V critical is RT critical. And the reason we are doing is, from the table we tend to get the value of pre-critical and T critical. That's why we are trying to convert this. V critical is equals to RT critical divided by P critical. So that's how we get reduced volume. So we have to know the values of reduced pressure and temperature and a specific volume to find the unknown property. That's why these definitions are important to us. Okay, so here, if you see here, this is kind of simplification of the compressibility chart, but we'll see the real chart which is given in the appendix A15. Okay, that's what we'll be using. But if the pre-critical, the pressure and temperature values are given, this is kind of simplified form. So in the on the x-axis you have pre-critical, which is P by, sorry, P reduced pressure, which is P by P critical. And this, see this plot, this is how it looks like. So these are the value of reduced temperature. So this the whole line is reduced 2, this whole line is reduced 1.5. So this is how it's moving. So it's very important. So if you want to find the value, so the goal is to find out the value of G. If the pressure and temperature are given, let's say we find the reduced pressure is 3, and then reduced temperature is 1.5, then you just do like this. So this is where it is. So this is 1.5, and this corresponding to this, you can find the value of G. So this is how you can use, if the pressure and temperature are given. Once you know G, then you can use the modified ideal gas equation to find the unknown. Okay, so that's how we do. And we discussed before as well, when the pressure is low here, like something like this, when the pressure is low on this side, it always behaves as ideal gas. If it is very close to this critical temperature and pressure, it does not show ideal behavior. So this point is very important. So if it's very close to this point, then the gas does not show ideal gas behavior. So we need to take into account the compressibility factor in that case. So these regions, because this region is away from this critical temperature and pressure, so even here it shows ideal gas property for any gas. So this is what we need to understand. It always relates to critical temperature and pressure. Close to the region, It does not show the um, idle gas behavior, but away from the critical pressure and temperature, it does show the idle gas behavior. So that's what we can understand from here. And as I was talking before, we need critical temperature, we need critical pressure, right? And these values are standard value, okay, so which we can get from the table, like so this is the point. So if this is temperature, we want to find out the critical pressure and temperature. And for different substance, for instance for ammonia, see, so it is table A1. From table A1 we get gas constant as well as the critical point temperature. So this is a critical point property. So this is the temperature in Kelvin, critical temperature, and this is critical pressure in megapascal. But see, for volume, see it's given in meter cube per kilomole. But most of the time when you are doing the calculation in SI unit, we want meter cube per kg, right? It's not given. That's why we get, you know, the reduce the critical specific volume from this equation, because if you know the temperature and pressure, then you can find out the critical. That's how we get using the equation. So so just be careful with this one, okay? So you can directly use the value of critical temperature and pressure from this table. For the specific volume, we can use the temperature and pressure relation to find the specific volume. Okay, so this is the chart, real chart that the one which I showed was kind of simplified one, but this is the chart which we have to use even for the exam. So this is figure A5. So this is in the appendix of the book, and if you see here, this is the x-axis which has reduced pressure. Reduced pressure is, as we defined before, is P divided by P critical. These critical values can be found from A1, and this line, as I showed before, so these all this line here, these are reduced temperature, which is T by T critical, and there are some more additional lines. See, these are V reduce. See, so you have pressure reduce, temperature reduce, and you need to be careful. So this is, so depending on what is given, you have to simplify the problem. And this one is kind of expansion from, so here you have 0. If you expand this is what it looks like. This is just zoom of this part. Okay, so you have from 0 to 1, which is reduced pressure. And if you do the calculation, if you find that the reduced pressure value is lower than 1, then I think it's better to use this one, because you get a more accurate value. Okay, so as I said before, if the pressure and temperature are given, then you can find out reduced pressure, and also the reduced temperature. After you get the intersection point, you can find out G. Then you can find once you know G, then you can find the specific volume. So the goal here is either pressure and volume is given, you need to find the temperature, or volume and temperature given, you need to find the pressure. So that's how we have to make use of this chart. So this chart is going to be very important. Okay, so there are three cases. So this is kind of concept map for solving ideal gas equation with a compressibility chart. If pressure and temperature is given, then we want to find the specific volume. Okay, so in that case, um, you can find PR and TR. So PR is x-axis, and TR is something like this. And if you know PR and TR, so you can get the intersection point, and corresponding that you get the value of G. And once you know the value of G, use in this equations. Okay, so um, R, you can get the value depending on what gas you have from A1, and if v and v is given, the value of z we just got from the chart, so the only unknown is specific volume. Okay, that's how you can calculate. The other option being pressure and volume is given in a problem and you need to find the temperature. Again, we need to make use of that compressibility chart. So find PR and VR. So PR is P by P critical, I think P critical, and the critical pressure can be found from A1. So if this is given, you can calculate the reduced pressure, and also so you can say this as volume. So reduced volume is V by R T critical pre-critical. So this value you can get from the table. This is table A1, right? And you can calculate VR as well. So our goal is to find the temperature. So for calculating the value of temperature, again, we are using the chart A15, and we know the x-axis is P reduce, which we got from here. And if you see this plot, so these are like T reduce, okay? But in this case, we know V reduce. So V reduce are something like this. If you see in the plot, let's say this is 0.1, then the intersection of this 0.1 and reduce pressure, for instance, could be like this here. So we found this intersection point. Once you know the intersection point, you can estimate like how much is um, T reduce at the intersection point. So from here we can find the T reduce, and once you know the T reduce, see here, T reduce is T by T critical. So our goal is to find out this one. From the plot we got this value, and T critical value we can get from A1. So the only unknown is um, 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 temperature, so we can use this equation to find the unknown temperature. So in this case, you don't even have to calculate the value of z, so you are getting directly the value of t using this plot. Okay, so this is the second case. Third case could be temperature and specific volume is given, you need to find the pressure. Again, it's all about making use of this figure A15 to get that. So calculate reduce specific volume, calculate reduced temperature because T and V is given. Once you know that, um, from reduced specific volume and reduced temperature, you can look at this intersection point, right? So if you think about this again, so these are reduced temperature and these are reduced volume. So depending on that, you can find the intersection point, and corresponding to that, you can find the x-axis is reduced pressure. So once you know the reduced pressure, critical pressure can be found from A1, appendix 1. So the only unknown is P. That's what we are interested in. So these are the three possibilities you have for finding the different unknowns. So either P and V is given, you need to find the temperature. When V and T is given, you need to find the pressure. At the beginning, we start with finding the reduced pressure or reduce a specific volume or reduce temperature, and once you get that value, find the intersection point, and accordingly you find the unknown. Okay, let's try to make use of this concept to do the calculation, and this is what the problem is all about. So you have so I think I'll discuss this in the next video. Okay.